Bismillahirrahmanirrahim. Dear students and viewers, in this video lecture we will discuss the idea of space-time. This is a central and very important idea of general theory of relativity, and we can say that this idea of space-time lies at the heart of GTR, general theory of relativity. First we will try to understand its very physical significance without getting ourselves in mathematical equations, and then we can discuss this somehow mathematically. Basically, we should observe, we should think of various situations to understand this concept. Let's consider two types of situations. In the first situation, consider a person who is standing in an elevator upon a weighing balance, or a weighing machine. The elevator is in free fall motion towards the center of the earth. That is, the elevator is within the earth's gravitational field, but the motion is free fall. So the weighing balance will read 0, and the astronaut or the person inside the elevator will feel weightlessness situation. Okay. In the second case, say the elevator lies somewhere in the upper space such that there is no net gravitational force on the elevator or the astronaut, and the elevator somehow starts moving up with some acceleration, say 9.8 meter per second square. Though there is no gravitational field, but the astronaut or the person inside the elevator will feel that his feet are stuck to the floor of the elevator with the same force as it was when he was standing on the surface of the earth. So gravitational force is basically a property that could be eliminated even in the presence of gravitational field of the earth or any other body, okay, like the one we did it in the free fall motion of the elevator. And this property can be created even in the absence of Earth's gravitational field or any other gravitational field. So hopefully you have got the idea, the notion of how to understand this space-time. So Einstein stated that this space-time is a property of the universal space. Okay, so we can create it, we can eliminate it, vanish it. So this property was named space-time. So what is the behavior of light within the space-time? Okay, because light, time and space, that they are connected together. So in this case we can say that the path of a light beam in three different frames of reference moving with respect to the ground-based observer. Suppose we are ground-based observer, so the light path shown is what the person inside the elevator sees. So in the first case, there is no motion. This elevator is stationary, and when the elevator is stationary and this person who is the outside person switches on the torch, so the beam of the light will just pass straight and will fall on the wall of the elevator. In the second case, the elevator is moving upward with constant velocity. There is no acceleration in this case. So the light beam will follow an oblique path and will strike some point which lies below the straight point, okay, below the one that was struck in the previous case. And in the third case, there is an accelerated motion, and this is very important to understand because in here the person is feeling a gravitational like force, okay, and the Wang scale is giving some weight reading of the person as well. So if a person switches on the torch and the light beam enters the elevator, so this person, the inside person, will observe a curved motion of the light beam, and it will strike the wall somewhere in here. So it means that once you create a gravitational force-like property, which we call space-time, then the beam of light will be curved. Okay, it will traverse a curved path. Right. Hopefully you would have got some idea of space-time. Now in the coming slide, I want you to watch a very important video, and this is related to again space-time and related to how to add time to the space coordinates. So we have a couple of videos in the coming slides. You please watch them out.
We have three spatial dimensions which we can label as X, Y, and Z. Every point in space can be described in terms of these three coordinates. However, there is nothing special about these three particular directions, and we can just as easily create a new coordinate system by rotating the axes. Every point in space can now be described in terms of the coordinates of these three new axes. Time is also a dimension. We therefore now have a total of 4 axes, but here we just show the axes for 2 of the 3 spatial dimensions, along with the axis for time. Every point in space and time can be described in terms of the coordinates along the 3 spatial coordinates and the coordinate along the time axis. When an object is moving along the time axis, it is not moving through space, but it is moving at the speed of light through time. As before, there is nothing special about these particular directions, and we can just as easily create a new coordinate system by rotating the axes. But the axis for time rotates differently than do the 3 axes for space. According to Einstein's theory of relativity, all observers can believe that they are standing still, and that it is the rest of the universe that's moving around them. This means that when an observer travels through space and time, their view of the axes for space-time are rotated in such a way so that they are moving exclusively along the time axis. But from their point of view, the axis for time is still at 90 degrees to the three axes for the three spatial dimensions, and it is everyone else's axes for time and space that have been rotated. Different observers will therefore disagree about the time and distance between different events. In traditional three-dimensional space, all observers could agree on the distance between points A and B, with the distance described by the following formula. No matter how the three spatial axes were rotated, the equation for distance always gave the same answer. In the theory of relativity, this is no longer true. But what all observers will now agree on is a new parameter called the space-time interval, described by the following equation. In the theory of relativity, different observers will disagree about the distance in space between points A and B. Different observers will also disagree about the time between an event that happened at point A and an event that happened at point B. But they will agree on this parameter called the space-time interval, which stays constant even as the axes for time and space are rotated. Light always travels along paths where the space-time interval is exactly 0 between every 2 points along the path. This means that all observers will always agree on the speed of light. No matter how the axes are rotated, the speed of light will always be the same for all observers. No matter how the axes are rotated, the speed of light will always be the same for all observers. Much more detailed information about Einstein's theory of relativity is available on the other videos on this channel.
So dear viewers, we can start the main theme of this video, in 2 points. The first point is that in classical mechanics, when we consider a vector of certain length, say L, and we specify an origin for that. Okay, so we have considered x, y and z space coordinates for that vector. Now, without moving the origin, we can rotate this coordinate system anyway, rightward, leftward, anyway we can rotate it, but the length of the vector will remain the same, though x, y and z values will change. So this is what classical mechanics says, that the length of the vector will be invariable with the rotation of x, y and z axes. But in general theory of relativity, this may not be true, because the space is not absolute. The space is relative in general theory of relativity. So what is that quantity that stays unchanged, invariable in general theory of relativity? This is space-time interval. This is not x square plus y square plus z square as it was in the classical mechanics. This is x square plus y square plus z square minus ct whole square. Okay, so let us see what the second value states.
Let's get a star. We'll put it in. And how can you lose energy if you have a planet going around the star? You know, you'd think there's no friction out in space. Mercury's just zipping around in outer space. But watch this. When I roll this ball, the only way that this ball knows how to roll is by the curvature of the fabric that it rolls over. You know, the fabric is bent, so it curves like that. So let's say that the planet rolls right over that square. By how that square is tilted and shaped, that pushes the ball around a little bit. But look at this. If I were to move the star, that piece of square fabric is like that. If I were to move it here, that piece of fabric is like that. There's a back and forth. As this rolls around, that fabric is doing things like that. But it doesn't do it instantly. If I were to move this star, it takes a certain amount of time for that information to get out to here. It's almost like a ripple. It's almost like as if you took a rope and went shoo, like that. That wave would just like propagate along a rope. Same exact idea. If I were to go shoo, like that, that ripple would propagate out. And if I had fabric that kept on going out, you know, like a zillion miles in every direction, and I did shoo, like that, it would, a wave of bending space-time would go out. That wave of bending space-time is what Einstein called a gravity wave, and as when you make any wave, you lose energy. And so, if you have a star doing like this, it's losing energy.
Right. So this was very interesting presentation and visualization of space-time. But remember, in here, this just happened in one way. Okay. Basically, what you have to think is that this space-time curvature, and this curvature basically happens because of the presence of a big, massive body. Basically, what mass is in general theory of relativity, the mass is basically the curvature of space-time. This is the first aspect of this description. The second description is that if we consider this space-time in this vertical way, because this is the horizontal way of presentation of space-time. If we consider it in vertical way, in this way, then you can have to think this sort of rubber sheet vertically, and even you can imagine it in here, like just in the front, in the side, another on that side, and even on the back side, and even everywhere. In all the directions you have considered this sort of scenario of space-time. So this is basically a four-dimensional continuum, or a four-dimensional fabric. And as the presenter stated in a very beautiful way, that once that body is rotated around its center of mass, like that, okay, so it produces ripples, waves in the space-time continuum, and that's how we can think of gravitational waves, okay. And now people are trying to detect, to observe these kinds of waves. So this is the sun that has made the space-time fabric curve in this way. And remember that the light beam always follow the space-time fabric, so that's why it's bended in here, and then it traverses its path towards the Earth. So there are many stars that we see in apparent location, like this is the apparent location of the star, but the actual location and position of the star is in here, and this happens because of the bending of light beam. And this is a normal star, because this bending of light requires a very strong gravitational field. So even a star cannot bend the light totally. So there is a very light bending that's hard to observe. So once we consider a neutron star, that's really a dense matter, revealing a very high gravitational field. So the bending of light beam is visible, and it has become clearer than the previous one. And this is a more massive neutron star with more matter, and hence more intense gravitational field. So the light beam follows again the space-time curvature that's curved more than the previous one. And as far as the black hole is concerned, as we know that light cannot escape from the black hole, and if a nearby illuminating object is emitting light, then all of the light will be captured by the black hole. So this is how we can think of space-time. And then this is more massive object, a heavy celestial object. This is space-time should be distorted into an infinite will by a dense black hole. The summary of this lecture is space, time, and energy are inextricably intertwined. We cannot separate them from one another, and all of the clocks run slow as a function of increase in relative velocity. Moving objects appear shorter in the direction of motion, as I stated it in the previous lecture, and also relativistic mass of an object increases as a function of increase in relative velocity. So hopefully you would have got the idea of this space-time, and conclusions of special theory of relativity and their description. If still you have any question, any query, so you can let me know about that. I wish you All the best and success in the future.